Find the critical points of f and then determine whether f has a local maximum, minimum, or neither at each of these points. And we're told that f of x is equal to x cubed minus x squared plus 3. So a critical point is just somewhere where there's something happening interesting in the graph. So it could either be a turning point or an inflection point. And in both of these cases, the first derivative is going to equal 0. So to find our critical points, what we have to do is take our first derivative and set it equal to 0. So doing that, we have that f prime of x equals 3x squared minus 2x. And then so we set this equal to 0. So 0 equals 3x squared minus 2x. And this is just like solving a normal quadratic function now. So we can factor out an x and get 0 equals x times 3x minus 2. And we get that x equals 0 and 2/3. So this is where the critical points are happening. Now at these points there might be a turning point or an inflection point. So to find out which one it is, we're going to have to take the second derivative. And so doing that, I'll change colors here for this. We get that f double prime of x equals 6x minus 2. So at inflection points, the second derivative is equal to 0. So I'm going to go ahead and set our second derivative equal to 0, and then solve for x. And you should get that x is equal to 1/3. So that tells us that there is an inflection point at x equals 1/3. So that means that's the only place where the second derivative is equal to 0. So both our critical points, 0 and 2/3, can't be inflection points if the second derivative isn't equal to 0 at those points. But to find out whether those points are local maxima or local minima, we have to plug them into our second derivative. So I'll go ahead and plug in our first critical point into our second derivative. So I'm going to look at x equals 0. So at this point, f double prime of 0 equals 6 times 0 minus 2. So that tells us that our second derivative at this point is equal to negative 2. Now let's plug in the other point. So the other point was x equals 2/3. So at f double prime of 2/3, we have 6 times 2/3 minus 2. And this comes out to be equal to 4. Sorry, equal to 2. So what does the second derivative tell us? So let's go ahead and take a look at just some generic graph of our first derivative. I don't know exactly what it looks like, but we already found that it equals 0 at x equals 0 and 2/3. So it might look something like this. Let's just pretend it crossed the origin there. So if this is our derivative, then I'm going to go ahead and plot our second derivative on there as well. So our second derivative is going to look something like that, because it's just a straight line. So we know that, or we found earlier that at this point, this is the derivative we're looking at, this parabola. We know that it's equal to 0 at the origin, and at that point, the second derivative is negative. So when the second derivative is negative, that tells us that our original function is concave down. And so over here, we found that it's equal to 0, the first derivative is, and then this is just a line, so our second derivative is going to continue out infinitely there. So we know that it's going to be positive, which we also found earlier. So that tells us that our first derivative, or our original function, is concave up there. So I don't know what our original function looks like exactly, but just based off of what we found, I know that at x equals 0, the function is concave down, so it might look something like this. And at x equals 2/3, it's concave up, so it might look something like this. So looking at that, you can tell right here that at x equals 0, we have a local maximum, and at x equals 2/3, we have a local minimum. So just some rules of thumb. If the second derivative isn't equal to 0 at your critical points, but it's positive, that means you have a local minimum, because that's where it's concave up. The graph is concave up. And then if the second derivative isn't equal to 0 at another critical point, but it's negative, then that means you have a local maximum, because the graph of the original function is concave down. So I hope this video was helpful. Go ahead and do me a favor and hit like and subscribe, and I hope you have a great day.